This is our video presentation for chemical engineering thermodynamics titled Pyrolysis Process Heating Rate under Ideal and Real Conditions.
Let me introduce our team and the roles for this presentation. I am Nur Atika binti Husaini. I'll begin with the introduction and explain the important formulas used in this study. Yong Zian will present the methods and calculation under ideal conditions. Ashraf Hakimi bin Hamda, Muhammad Danish Harid bin Adlan, and Hani Najiha binti Harun will explain the methods and calculation under real condition. Also, Hani Najiha will deliver the conclusion summarizing our key findings. Hi everyone, I'll be introducing our project on pyrolysis technology for plastic waste management. Plastic waste is a serious environmental concern, and pyrolysis offers a practical solution by converting plastic like HDPE into valuable products such as hydrogen, methane, oil, and charge. This is done by heating the plastic in an oxygen-free environment. In this study, we are focusing on the thermodynamic aspect of the pyrolysis process. Since pyrolysis requires high temperatures, understanding the heating rate at 500 degrees Celsius is crucial. This goal is to compare the energy needed under both ideal and real conditions, which can help improve efficiency and guide future application. With that, I will now pass it on the next part, the calculation of the heating rate. Okay, now let's go over some important formula used in this project. The first one is enthalpy change equation. This calculates the change in enthalpy as temperature increases using the heat capacity. This extended form includes temperature dependent terms to give a more accurate enthalpy change for nonlinear system. The second one is mole balance equation. This helps in calculating the change in moles of different species during duration. This equation includes reduced temperature pressure to model the behavior of real gases more accurately. The last one is heat duty. This calculates the total energy or heat required during the pyrolysis reaction.
My name is Yong Ziyan and I will continue the presentation. In this process, the reactant is HDPE C2H4 3 and the products are hydrogen H2, methane CH4, ethylene C2H4 and propylene C3H6. Let's start with calculations for ideal condition. First, a hypothetical path is drawn. From the hypothetical path, delta H1 is calculated by using the standard heat of formation Hf for each reactant and product as this path is at ideal condition. Delta H2 is calculated by CpdT because this path involves change in temperature from 298 Kelvin to 773 Kelvin. For delta H1, the Hf of HDPE C2H4 3 is calculated by referring to reference, while for the Hf of the products, they are obtained from table C4. Next, delta H1 is calculated by sum of Hf of products minus sum of Hf of reactant. Then multiply with 1 mole to get negative 66.83 kJ, as the unit requested in the question is kilojoule. The number of mole is from the stoichiometry of the equation. Next, for delta H2, formula of CpdT is used. The value of A, B, C, and D for each product that obtained from table C1 are listed in the table. Through the stoichiometry, we know that each product has 1 mole. Then substitutes the sum of A, B, C, and D into the equation 4.8 and multiplies with gas constant. The delta H2 is 114.082 kJ. Last, add the delta H1 with delta H2 and the heat calculated is 47.252 kJ in ideal condition. This is table C4 which state the values for standard heat of formation and table C1 which state the value of A, B, C, and D for heat capacity calculations for each component.
This slide explain the methods and calculation used under real gas condition. First, we draw the hypothetical path for the real condition. We started with the reference condition at 298 K and 1.0133 bar and calculate the enthalpy change to the final condition at 773 K under the same pressure. For this system, we calculate the total enthalpy change, delta H, by considering two main contributions. First, the sensible heat change, that represented by the heat capacity integral, and second, the deviation from the ideal gas behavior, which is accounted for by the residual enthalpy values. First, for reactant C2H4, we use the corresponding state methods, where reduced temperature TR and also reduced pressure PR are determined based on the critical properties of the component. This value allows us to calculate the residual enthalpy correction factors. We use equation 6.66 to find the values for HR. First, we need to find the values for HR0 and also HR1. The values for X and also Y can obtain from the table B to find the values for HR0 and also HR1. We need to calculate the residual enthalpy HR because real gases do not behave like ideal gases, especially at high temperature and also pressure. Final values we obtain for H.R is negative 23.359 kJ. Next, the product C2H4. We also need to use the corresponding state method, where reduced temperature TR and also reduced pressure PR are determined based on the critical properties of the component. This value allows us to calculate the residual enthalpy correction factors. We need to find the values for HR0 and also HR1 to find the total for HR. The values for X and also Y can obtain from the table D. And the final values for HR is negative 0.014 kJ.
Okay, now next. This slide shows the determination of reduced residual properties for methane. This is very important in order to calculate the residual enthalpy, which will later be used in order to calculate the heat. Firstly, we go to table D1 and find the value for omega, TC, and also PC. TC and PC are very important because we need to find the value for TR and PR using the formula TR over T over TC and PR equals to P over PC. PC and TC stands for critical temperature and critical pressure. Meanwhile, TR and PR stands for residual temperature and residual pressure. Next, in order to calculate the value for HR0 over RTC and HR1 over RTC, we go to table D5 and D6. Yeah, and here I have highlighted four values for both HR0 over RTC and HR1 over RTC. We need to do some extra work. We need to do two extrapolations and one interpolations, since our value for TR and PR is not directly available in the table. And after our lengthy calculations, we find that the value for HR0 over RTC is 0.002056 and the value for HR1 over RTC is 0.0040. Okay, next, as for propylene, it is just the same as the previous one we did for methane, but the HR1 over RTC for propylene at TR is 2.114 is assumed to be 0.001, since the value for HR1 over RTC from residual temperature at 1.9 until 3.00 is 0.001, which means that the value is constant at this range for residual temperature at this point. So yeah, the value that we get after the interpolations is HR0 over RTC is negative 0.0055 and the value for HR1 over RTC is 0.0019. Okay, and finally for hydrogen, we repeat the same steps as the methane one and we will get the value of HR0 over RTC equals to 0.07354 and the value for HR1 over RTC is 0.04256.
Now, I'm Hani Najia will be presenting the last step for this presentation. Before we move on to the last step, we need to total up all the residual enthalpy at product side. Here, negative 0.656 for CH4, negative 16.21 for C3H6, 17.76 for H2, and negative 0.014 for C2H4. So we get negative 0.013 kilojoule. So the heating rate during real condition is residual enthalpy of the reactant plus sum of change of enthalpy 1 and 2 plus residual enthalpy of product. For your information, the meaning of negative value at last calculation here is because it is from reactant side. So negative of negative 23.359 plus 47.252 plus negative 0.013 is 70.598 kilojoule. To sum up all the calculation, the heating during the pyrolysis process is 47.252 kilojoule for ideal condition, and for real condition is 70.598 kilojoule. Real systems are far less efficient due to energy losses and reaction dynamics that are often ignored in ideal models. It is necessary to understand this theoretical for designing more efficient pyrolysis systems, like calculate real heating needed, reduce energy used in pyrolysis process, optimize reactor design, and improve the overall sustainability and economic availability of biomass pyrolysis technologies. And for the reference, we are referring these two reference book and website for all the data table we use above. That's all from us. Thank you.